Hi and welcome back to class of Design of Machine Elements. I am Hitesh Raiyani, Assistant Professor at LJ Institute of Engineering and Technology. This is lecture 25, Length of Flat Belt. The learning outcomes of these lectures is to learn the derivations of length of flat belt drives, and also we will see one examples based on the belt drive. In previous lectures we learned the velocity ratios and how to get the velocity ratios according to the belt drive system. So in these lectures we learned one example based on the velocity ratios. So first of all we derive the length of belt for the open belt drive. So length of an open belt drives, and for that we have to consider one open belt drive systems as shown in here. So here the bigger pulley shows the radius of R1 and the smaller pulley has the radius R2, and the distance between these two pulleys is as considered as X. And all these configurations as we see in figures we have to taken to derive the length of the flat belt drive. Now R1 and R2 is the radius of larger and smaller pulley radius, and X is the distance between the center of these two pulleys, that is O1 and O2. So O1 O2 distance is considered as X, and L is the length of the belt. So our aim is to derive the equations of length of belt for the open belt drive system. So here we consider the systems, and according to it we have to consider the we have to derive the length of belt. So for that we have to start from any one point and we have to follow the length of belt to calculate the equation. So here as we start from the arc GJE, so we get the length of belt L is equal to arc GJE, then followed by the distance EF, then followed by the distance arc FKH, and then followed by the distance HG. So if we go around this belt, then we can find the length of the belt is equal to arc GJE plus EF plus arc FKH and distance HG. So we get the equations in terms of arc GJE, HG, EF and arc FKH. Now if we see the configurations, you can see that the arc GJE is nothing but the 2 times the arc JE, and if we see the smaller pulley arc, that is arc FKH is equal to 2 times the arc FK. And you can see that in figures there are equal distance, EF is equal to HG. So EF and HG distance is the same as per our configuration. So we have to write HG is equal to EF. So if we place these values in our equations, we get 2 times the summation of arc JE, EF and arc FK. So we get the L is equal to 2 into arc JE plus EF plus arc FK. Now we have to calculate the sin alpha, and for that we have to consider the triangle O1M02. And from these figures you can see that sin alpha is nothing but the O1M divided by O1O2, and O1M, if you consider the distance O1M, that is nothing but the R1 minus R2. So we have to place this value in these equations, and O1 O2 distance is considered as X. So the final sin alpha becomes R1 minus R2 divided by X. And here the alpha value is very small, so we have to consider sin alpha is equal to alpha in our case. So we get the length of arc GJE or arc J. Here we have to find the length arc length JE. So arc JE is nothing but the R into theta. And if you see the pictures, there are the theta value is nothing but the pi by 2 plus alpha. So the angle value of theta we have to consider as pi by 2 plus alpha, and radius R is considered as a R1. So we get the arc JE is equal to R1 into pi by 2 plus alpha. Similarly, that we have to consider the arc FK, and for that if you will see that here the angle theta is pi by 2 minus alpha. So here we have to take theta is equal to pi by 2 minus alpha, and RE we have to consider as R2. So we get the arc FK is equal to R2 into pi by 2 minus alpha. So according to the length of belt, we need this both arc value, and also we need the value of EF. So now we have to calculate the value of EF, and for that we have to consider the triangles O1 and O2. And if we see in figures here, the distance MO2 is equal to the distance EF. So EF is equal to MO2 is equal to under root of O1 O2 square minus O1 M square. And here O1 O2 is the distance between two pulleys. So it is x. So x square minus O1 M is R1 minus R2. So R1 minus R2 raised to square. And if we simplify these equations, we get EF is equal to x into under root 1 minus R1 minus R2 divided by x raised to whole square. So we have to expand these equations up to two terms. So we get the EF is equal to x into 1 minus 1 half R1 minus R2 by x raised to whole square. And if we simplify multiply x with bracket, so we get the EF is equal to x minus R1 minus R2 raised to whole square divided by 2x. So this is the equations of EF. Here we consider only two terms in the expansion series. Now we have all the value of arc JE, arc FK, and distance EF. So we can calculate we can derive the equations of length of belt. Now we have to just place the value of this all in our equations. Our equations is L is equal to arc 2 times arc JE plus EF plus arc FK. Now we have a whole value of arc JE, distance EF, and arc FK. So placing these all values, we get the length of equations like L is equal to 2 into R1 into pi by 2 plus alpha plus x minus R1 minus R2 square divided by 2x plus R2 into pi by 2 minus alpha. Now in these equations we have to simplify. So if we multiply R1 and R2 in bracket, so we get equations like this. And we know these equations have to simplify by considering the common terms of alpha and pi by 2. So we get the L is equal to 2 into pi by 2 into R1 plus R2 plus alpha into R1 minus R2 plus x minus R1 minus R2 raised to whole square divided by 2x. So L is equal to pi into, if we multiply 2 in bracket, so we get L is equal to pi into R1 plus R2 plus 2 alpha into R1 minus R2 plus 2x minus R1 minus R2 square divided by x. So this is the length equations, and we have to further modify, simplify it. So for that we have to place the value of alpha is equal to R1 minus R2 divided by x. So we have to place this alpha value in our previous equation. So we get the L is equal to pi into R1 plus R2 plus 2 into R1 minus R2 divided by x into R1 minus R2 plus 2x minus R1 minus R2 raised to square divided by x. So if we simplify these equations, we get the equations like this. And furthermore, if we simplify, we get the length of belt L is equal to pi into R1 plus R2 plus 2x plus R1 minus R2 raised to square divided by x. So this is the length of belt for the open belt drive systems, and this equation is in terms of radius of pulleys. So you can write also the length of belt in terms of diameter of pulleys. So in terms of diameter of pulleys, you can write L is equal to pi by 2 into d1 plus d2 plus 2x plus d1 minus d2 raised to whole square divided by 4x. So this is the final equations of length of belt for the open drive. Now consider the example based on the velocity ratios. So example 1 is an engine running at 150 rpm drives a line shaft by means of belt. So here the engine pulley is running at 150 rpm. The engine pulley is 750 mm diameter and pulley on the line shaft is 450 mm. So here the diameter of pulley is given, that is 750 mm engine pulley and 450 mm for the shaft pulley, and a 900 mm diameter pulley on the line shaft drives at 150 mm diameters pulley key to the dynamo shaft. Find the speed of dynamo shaft when there is no stretch. So according to these configurations, here the configuration is as compounding belt drive. So first of all, we collect the data given, that is N1 is equal to 150 rpm, D1 is equal to 750 mm, D2 is equal to 450 mm, and D2 is equal to 900 mm, and D3 is equal to 900 mm, and D4 is equal to 150 mm. According to these given problems, you can see in figure according to our problems. So here you can see the engine shaft, line shaft and dynamo shaft. Also the pulley created with this shaft, that is engine shaft pulley is 1 and line shaft there are 2 pulleys mounted, pulley 2 and pulley 3, and pulley 3 drives the dynamo shaft pulley that is mounted at the dynamo shaft and it is denoted as pulley 4. So here what is our aim is to find the dynamo speed of dynamo shaft. So here we have to calculate the speed of N4. So as we know, this is the compound compound belt drives, and we know the according to this data, the compound for the compounding drive, the velocity ratio is N4 upon N1 is equal to D1 into D3 divided by D2 into D4. Here we have all value D1, D2, D3 and D4, and also we have a value of N1, that is the speed of engine shaft. So that is equal to given is 150 rpm. So if we place this all value in these equations, that is 150 revolution per minute is equal to N1, D1 is equal to 750 mm, D3 is equal to 900 mm, and D2 is equal to 450 mm, and D4 is equal to 150 mm. So if we get that, we get N4 divided by 150 is equal to 10. Now we have to calculate the N4. So N4 is 150 into 10. So N4 is equal to 1500 rpm. That is our answer. That is N4 is the dynamo shaft speed. So in this lectures we derive the length of belt for the open belt drives, and also we learn one example based on the velocity ratios for the compound belt drive. Thank you.